Welcome to Echoes of My Imagination. My name is Tracy Lee. Sit back, relax. Let me tell you a story. Today's story is part 8 of How the World Works. Let's get into it. Nuclear fusion and fission. I am the energy held within the nucleus of atoms. Most appear stable. Atoms combine into molecules. Molecules build minerals, water, air, and living tissue. These structures change through chemistry, but the nuclei of atoms usually remain untouched. Inside those nuclei, however, enormous energy is stored. Protons and neutrons are held together by the strong nuclear force. This force binds the nucleus with tremendous strength, yet the arrangements of these particles determines how stable the atom will be. When the nucleus changes, energy can be released. This energy appears through two opposite processes. Fusion joins smaller nuclei together. Fission breaks larger nuclei apart. Both release energy because the final arrangement of particles holds slightly less mass than the original one. The missing mass is not lost, it becomes energy. The relationship between mass and energy is exact. A small amount of mass can produce a large amount of energy when converted, according to the relation above. Inside stars, fusion dominates. At the center of a star, temperatures rise to millions of degrees. Matter exists as plasma, where atoms have been stripped of their electrons, and nuclei move freely through intense heat and pressure. Under these conditions, hydrogen nuclei collide with enormous energy. When two hydrogen nuclei overcome their natural electrical repulsion, they fuse together to form heavier elements. Through a chain of reactions, hydrogen becomes helium. Each step releases energy. That energy moves outward from the core of the star as radiation and heat. After traveling through layers of dense plasma, it escapes into space as light. Every sunrise on Earth is the distant result of fusion reactions occurring deep inside the sun. Over time, as hydrogen becomes scarce in the core, stars begin fusing heavier elements. Helium can combine into carbon. Carbon may fuse into oxygen and still heavier elements. The elements that make up planets, rocks, and living bodies were forged through these reactions inside ancient stars. Fission moves in the opposite direction. Certain heavy atoms, such as uranium, contain large nuclei that are only marginally stable. When one of these nuclei absorb an extra neutron, it may split into two smaller nuclei. When the nucleus divides, additional neutrons are released along with a large amount of energy. Those neutrons can strike nearby atoms and trigger further divisions. Under the right conditions, a chain reaction forms. Each split releases stored energy within the original nucleus. In nature, fission occurs slowly and radioactive materials such as unstable nuclei decay over time. In controlled environments, humans have learned to guide this process within nuclear reactors, where the released energy heats water and produces electricity. Both fusion and fission reveal the same underlying truth. Atoms are not indivisible building blocks. They contain deeper structures where force operates with extraordinary strength. When those structures rearrange, the change releases energy that once helped hold the nucleus together. In stars, fusion lights the universe. In rare, heavy elements, fission slowly reshapes unstable nuclei. Through these processes, matter and energy transform in ways far more powerful than ordinary chemical reactions. The warmth of sunlight, the formation of elements, and the deepest energies within atoms all arise from these nuclear changes. I am the transformation of the atomic nuclei. I am fusion and fission. Superconductors. I am the path with no resistance. I am superconductivity. Electric current normally struggles as it moves through matter. In ordinary metals, electrons travel through a lattice of atoms arranged in a repeating pattern. As the electrons move, they collide with those atoms. Each collision steals a small amount of energy from the moving charge. That lost energy becomes heat. This resistance limits how efficiently electricity can move through wires. Power stations must generate more energy than is ultimately delivered because some of it disappears as heat along the way. But under certain conditions, matter behaves differently. When some materials are cooled to extremely low temperatures, the electrical resistance inside them suddenly vanishes. Current can move through them without losing energy. The flow becomes perfectly efficient. This phenomenon was first observed in 1911 by Dutch physicist Heike Kamerlingh Onnes. While studying mercury cooled near absolute zero, he discovered that its electrical resistance dropped abruptly to zero. The metal had entered a new state of matter. In this state, electrons no longer moved independently through the material. Instead, they begin to move in coordinated pairs called Cooper pairs. These paired electrons behave differently from single electrons. They move through the crystal lattice as a collective wave, rather than as individual particles colliding with atoms. Because of this coordinated motion, the usual collisions that produce resistance no longer occur. The current flows without friction. Another remarkable effect appears at the same time. When a material becomes superconducting, it expels magnetic fields from its interior. This behavior is known as the Meissner effect. Magnetic field lines bend around the material instead of passing through it. If a magnet is placed above a cooled superconductor, the magnetic field cannot penetrate the surface. The interaction between the magnet and the expelled field can cause the magnet to hover above the material. The magnet appears to float. This phenomenon demonstrates how strongly superconductors interact with magnetic fields. The same property allows them to produce extremely powerful magnetic forces when electrical current flows through superconducting coils. Because resistance is absent, the current can circulate indefinitely once it is started. In laboratories, superconducting loops have maintained electrical currents for years without any additional energy input. The only challenge is temperature. Most known superconductors require extreme cooling, often only a few degrees above absolute zero, where atomic motion becomes minimal. To reach these temperatures, scientists use liquid helium or liquid nitrogen. Cooling systems make superconductors complex and expensive to operate. However, in the 1980s, researchers discovered a class of materials known as high-temperature superconductors. These compounds became superconducting at temperatures far warmer than earlier materials, though still extremely cold by everyday standards. Many of these materials are ceramic crystals containing copper and oxygen. Their behavior is not fully understood, but they demonstrate that superconductivity can exist under less extreme conditions than once believed. Because superconductors can carry electricity without loss, they offer remarkable possibilities. Power transmission lines made from superconducting materials could move energy along distances with minimal waste. Medical imaging systems known as MRI scanners already use superconducting magnets to generate strong, stable fields. Particle accelerators rely on superconducting magnets to guide beams of charged particles along precise paths. Perhaps the most striking demonstrations appear in transportation. Some experimental trains use superconducting magnets to achieve magnetic levitation, often called maglev. Instead of resting on wheels, these trains float slightly above the track as magnetic forces hold them in position. Without friction between wheels and rails, the train can move with extraordinary smoothness and speed. Superconductivity reveals something fundamental about matter. At everyday temperatures, atoms vibrate constantly. These vibrations interfere with the orderly movement of electrons, but when the material becomes cold enough, those vibrations slow dramatically. Under the right conditions, electrons begin moving in coordinated patterns that allow them to slip through the lattice without scattering. The material enters a new quantum state. Across the microscopic structure of the crystal, billions of electrons behave as a unified system rather than individual particles. This collective behavior shows how quantum physics can appear on a visible scale. A ring of superconducting wire carrying current is not merely a collection of electrons moving randomly. It is a synchronized wave of charge moving through matter with perfect efficiency. Energy flows without loss. Magnetic fields bend and reshape around it. In this state, matter reveals a form of order normally hidden by the chaos of thermal motion. I am the silent path where electricity meets no obstacle. I am superconductivity. Space. I am the vast region between worlds. I am space. To the eye standing on Earth, the night sky appears quiet and empty. The darkness between stars looks like nothing at all. Yet space is not truly empty. It contains particles, radiation, magnetic fields, and the faint remains of ancient events that occurred billions of years ago. Even the darkness carries information. Between stars drift cosmic dust, tiny grains of carbon, silicates, and ice. These grains are often smaller than smoke particles. They form when stars age and shed their outer layers, or when supernova explosions scatter heavy elements into surrounding space. Over immense spans of time, these particles gather into clouds. Within these clouds, gravity slowly draws matter together. New stars ignite, and around them planets begin to form. Much of the material that exists on Earth, iron in blood, calcium in bone, carbon in every living cell, was once part of this drifting dust. Space is therefore not only emptiness, it is the birthplace of stars and worlds. Amongst the most visible travelers moving through space are comets. Comets begin far from the sun in distant regions known as the Kuiper Belt and the Oort cloud. In these remote areas, billions of icy bodies remain from the earliest formations of the solar system. They are often described as frozen mixtures of ice, rock, and dust. When a comet's orbit carries it towards the sun, sunlight warms its surface. Ice begins to vaporize, releasing gas and dust into space. The escaping material forms a glowing cloud around the comet called a coma. The solar radiation and the solar wind then push this material outward. The result is a long, luminous tail that may stretch millions of kilometers across space. These tails always point away from the sun, not behind the comet, because they are shaped by streams of charged particles flowing outward from the star. For centuries, comets appeared unpredictable and mysterious. Ancient observers sometimes interpreted them as omens. Only later did astronomers realize they followed long elliptical paths around the sun. In 1705, Edmund Halley studied historical observations of comets and recognized that several sightings were actually the same object returning repeatedly. That comet now bears his name. Its orbit brings it past Earth roughly every 76 years. Space contains more than solid objects and drifting dust. It also carries waves and particles traveling across enormous distances. For most of human history, the universe was studied using only visible light. Telescopes revealed stars, planets, and nebulae. but the sky seemed limited to what the human eye could detect. During the 19th and 20th centuries, scientists began to realize that light visible to human eyes is only a small portion of a much larger spectrum. Light itself is a form of electromagnetic radiation. These waves travel through space at the speed of light but differ in wavelength and energy. Radio waves have long wavelengths and low energy. Visible light occupies a narrow middle band. Beyond it lie ultraviolet radiation, X-rays, and extremely energetic gamma rays. Each type reveals different information about the universe. Radio waves allow astronomers to detect cold clouds of gas drifting between stars. Infrared radiation reveals warm dust where new stars are forming. X-rays and gamma rays expose violent cosmic events, such as exploding stars or matter falling into black holes. Modern astronomy studies the universe across the entire electromagnetic spectrum. But electromagnetic radiation is not the only signal arriving from space. In 1912, the physicist Victor Hest carried sensitive instruments high into the atmosphere aboard a balloon. As he rose higher above the Earth, he expected radiation from the ground to decrease. Instead, the radiation increased. Hess had discovered cosmic rays, high-energy particles arriving from deep space. These particles, often protons or atomic nuclei, moved close to the speed of light, strike Earth's atmosphere, and produce showers of secondary particles. They carry information about powerful events occurring far beyond our solar system, including supernova explosions and energetic processes near black holes. Later discoveries expanded the list of signals reaching us from the cosmos. In 1964, radio astronomers Arno Penzias and Robert Wilson detected a faint microwave glow coming from every direction in space. This radiation became known as the cosmic microwave background. It is the cooled remnant of energy released shortly after the universe first formed. The faint signal provided strong evidence supporting the theory that the universe began in a hot, dense state, often called the Big Bang. More recently, scientists have detected gravitational waves, ripples in space-time produced when massive objects such as black holes collide. These waves stretch and compress space itself as they move outward from their source. With this discovery, the universe can now be studied not only through light and particles, but through the movement of space itself. Space, therefore, sparks through many channels. Light waves carry images of stars and galaxies. High-energy particles strike the atmosphere from distant explosions. Microwaves whisper the memory of the early universe. Gravitational waves ripple outward from cosmic collisions. Each signal travels across immense distances before reaching Earth. Across the darkness between stars, information moves continuously. The universe is not silent. It is filled with motion, radiation, and matter drifting through the vast spaces between galaxies. Dust gathers into new worlds. Comets wander through solar systems. Waves of energy cross billions of light years before touching the instruments of the observers on a small planet. I am the immense stage where stars are born, worlds travel, and signals from distant ages arrive. I am space. And that's it for today. Thank you for joining me for Echoes of My Imagination. My name is Tracy Lee. Don't forget to subscribe, share, like, and follow, and I'll catch you next time.